Hello. Yeah. Okay. Should we start? Okay. So I'll briefly start with the introduction of Turing machine, and then we will discuss the problems. Okay, related to Turing machine. So let me start. I hope recording started. Yes. So we are conducting this particular session under the Prerna scheme, which is organized by our college for specifically SC/ST students, and its benefit can be taken by all the students. So myself, Mrs. Gyankamil Chhajed, I'm going to present a session on subject theory of computation, and in this session I'll be discussing about theory of Turing machine, which is one of the more powerful or most powerful machine. And in this we will be discussing about the basic uh, structure of Turing machine, its working, and then we will be solving some problems based on different uh, problems which are solvable by the Turing machine. So let us start. So here I'll be presenting screen. Just let me know whether it is visible or not. Hello? Yeah. So, uh, so we'll start with the Turing machine. So I hope my screen is visible to you. Yes. So we'll start. So what is a Turing machine? So Turing machine is a machine which is named after Alan Turing, who is great mathematician and called the inventor of this machine, who has specified that every computer can be simulated as a Turing machine, and every Turing machine can be represented by computer program which are solved by Turing machine can be solvable by every computers. Okay. So now we'll very first look at the properties of Turing machine. So since we have to cover much of the part, we'll be using my notes and we'll discuss whenever it is required. So this is just the refreshment. So finite state control similar to finite state machine. since any program needs a finite number of functions and states. So here, very basic machine. Okay, so please message if you are not able to listen me. Otherwise, it is creating noise here. Okay. So, Turing machine, we have already seen that the finite automata is represented as a state, and in this state, we are having multiple cells, okay, and we are having a control which is attached to a head, and this control is representing the current state. Now, in case of finite automata, the head can move into the only right direction. It can only read the things and it cannot write. Okay. So these are the limitations which makes the finite automata limited for solving limited problem. Okay. So to have more range of problem solving, we are available with more powerful machine, that is a Turing machine, in which we have that the head can move in either direction, that is either left or right. Okay, it can not only read but it can also write on the same. Next, it is having infinite size. It is called to be having infinite memory. Now we are saying that finite automata is having no memory because it cannot remember. So what exactly this means? It cannot revisit the existing red cells, while in case of Turing machine we can have the reading of existing or already read cells, and that is possible because this head is having way of moving towards left as well as right, or it can even stay on the same place. So this mechanism of Turing machine makes it more powerful to solve many range of problems. Now here we are having finite state control similar to finite state machine, since any program needs a finite number of functions or states. So we need to have a machine, that is Turing machine, which will be having finite number of states. Next is external memory capable of remembering arbitrarily long sequence of inputs. To achieve this, the machine should have unbounded one-dimensional memory from which it can choose any required part by moving left, right, or staying in one position. So the entire unbounded state act as infinite memory. As I have told you, it is having a more range of cells to store the information. Next is ability to store, that is write on tape. So whenever we are storing, actually we are writing. Okay. So the machine head should be read and write head. So read head is modified as read write head. Next is ability to consume its own output as input during the execution. 1 minute. See, if any issues with the lecture, you can write message so that I will not accept any of the call. Okay. So ability to consume its own output as input during execution. 1 minute. Okay. So ability to consume its own output as input. So basically the problems where we are doing multiplication, finding GCG, like this problem solving, we require the intermediate results as input for the next step. So this is possible in the Turing machine. So ability to consume its own output as input during execution. For all this, the intermediate results information must be stored at memory. So these are the some Turing machine properties. So now we will see the structure of this Turing machine. Quickly we will revisit. So just now I have already shown you the Turing machine elements. So as it is shown, you can have infinite blank tape in both sides. This head can move left, right, okay, and this finite control is keeping the information of current state. Now, how we represent a Turing machine? So we represent Turing machine with the help of the M, which is representing machine, and we are having separate seven tuples. Okay, so Q represents state, summation stands for input symbols. Okay, which is subset of tau. Now, what is it tau? Tau is nothing but all allowed possible symbols on the tape, including the blank characters. So whatever you can read, write, or write on the tape, all is considered as the set, which is represented by this sign. Okay, so this will be your subset input symbol. Next is the delta function is representing your state function. Q0 is representing your initial state. B is representing a spatial symbol which is representing a blank character. It depends which character you want to use. And F is representing the set of final state. So in Turing machine, we generally use the halt state word for representing final state. Okay. So which is again a one of the state or in the finite set, that is Q. So 1, 2, 3, 4, 5, 6, 7 parameters are representing the Turing machine. Now, what is a delta function? So delta function in case of finite automata, we have seen the output is dependent on, that is Q, okay, into input symbol is giving you next state. That's it. But in case of the Turing machine, we are having a delta function in which we are considering whatever possible symbols on the uh, tape is considered with the all states. Okay, so it is going to give you information about what will be the next state, what will be the symbol which will be written on the tape on the same cell, and whether the head will be moving left, right, or no movement. So whenever we are having any state and reading any symbol, okay, we are getting three information as a function matrix which is representing next state, the information to be written, and the movement of the head. So TM is denoted with the help of three functions, namely MAF, that is a machine function, which is representing output. Okay. STF state function and DIF is representing a direction function. So MAF I into S is giving you I. Okay. That means what I is representing here, I is nothing but here Q. Okay. And S is representing, sorry, I is your input symbol and S is your states. Okay. So it is giving you whatever symbol you are going to write on the tape as an output. Okay, so here I is will be your top because here you will be having all input symbol as a subset of top. Okay, so here whatever you are writing, that is going to be also a part of top. STF function, the combination of tau and the state, the same thing, you are getting the next state, that is this Q, and DIF is representing again state and the symbol to be read. So this is here I and this is here S. Okay, so it will give you the information either L, R, and N. Now, this action can be described collectively by an ordered set of five elements, that is a quintuple, that is A, alpha, B, beta, and L, where A will be your input, which is whichever is the red symbol. One minute. Okay, so with the five tuples, we are representing the status of the Turing machine. That is, A is representing input symbol, alpha is representing your current state, B is representing what you are going to write on the tape, okay, and this beta is representing your next state, and L is representing the direction. So these two parameters are representing this Q and alpha, this Q and top, and these three values are representing these three values. Okay, so we represented this quintuple with the table called as transition matrix, or it is also called as functional matrix. Now, how this functional matrix looks like? So the functional matrix looks like this. We are having here the matrix in which we are having here all the symbols which will be read, and here we will be having all the states. Now here all the five tuples are represented like this: current state, current symbol, and next three is next state. This is your next state, this is your written symbol, and this is the direction. So in this way, the five information is represented in the functional matrix. Now, as we can see in this example, the current state and the next state is same. The current symbol and written symbol is also same. So in this case, we can minimize the representation of the next state of the Turing machine in the reduced form or simplified form. Instead of representing every entry in the form of three variables, we are representing only entry which is changing, which is updating. So here, this I into S is giving you I into S into D information. So in simplified functional matrix, we are having the current state, the current symbol, and only R is written because these are the same thing which are not changing. The current state and next state is same. The red symbol and written symbol are also same. So only whatever is new thing is written here, that is a direction information. So direction information is must in this simplified functional matrix. Now, if we say this example here, the current state was alpha, next state was beta, current value read was 1, but written value was 0. So there is a change in everything. The state is also changed. The written symbol is also changed. So here we have represented this entry with the three tuples. Okay. So likewise, we are representing a working of a Turing machine with the help of a functional matrix, and to be in a simplified form, it is represented with the simplified functional matrix. Now, how we write the delta function in this case? So, delta a comma alpha. So, what is a here? In this example, a is acting as 0. Okay, alpha is representing the current state. Okay, I hope I am audible. Yes. So, here we are having the next information as what? A, alpha, and R. Okay, in case of what? If it is not changing. So in this example, it is 0 and alpha. So it is giving you next information as 0, alpha, and R. Okay, it can also be written in the simplified way like this. Now, as we know that generally we have a good understanding of any machine with the help of transition graph. So how we represent Turing machine with the help of transition graph. So in case of transition graph, we are having the states in the circulars and circles, and the transitions are represented with the arrows. Okay. Now it is as similar as in all finite automata, finite state machine. So it is necessary you should represent starting state with the initial arrow to the first state. Okay. So in this example, alpha is acting as the initial state, which is represented here with this sign. Okay. Now we will simulate this particular functional matrix with the help of this transition graph. So we'll have it three states, so alpha, beta, and gamma. Now we will show the transition. So alpha on 0, okay, is moving to right. So since there is no change in state, there is no change in the return value, you will be having 0. This particular is representing that alpha on reading 0, okay, moving towards right. That indicates, and the loop is to self state, so it indicates there is no change in the state. Same way, when alpha is reading 1, it is changing all the parameters. So it is changing the state to B. So the arrow will be from alpha to beta state. So on alpha on reading 1, it is giving you information as 0 to be written and moving towards right. So in many literature, you may find different notations to represent this particular. They may write even like this 1 comma 0 r. So you should understand that 1 is read and written is 0 and the movement towards right. Same way, alpha on blank is moving towards right, which is shown with this self arrow. And then finally, beta on 0 and 1 don't move anywhere, but beta on blank is moving to the next state, that is a gamma state. Okay, and there is no movement. Okay, and finally you are having a gamma state where there is a blanks. It indicates that there is no movement for noted for this particular state. So here this gamma state is noted as halt state, hence it is required that near to this particular state you should mention halt. Okay, so as soon as you reach to this halt, starting from the initial state, you will say that your machine working is over, it's stopped. Okay, so I hope you understood the representation of Turing machine with the help of the transition graph. Now we are moving to IDs. So again, questions can be asked related to this ID, the paper. So what is this ID? ID of TM is nothing but instantaneous description of a Turing machine, and which is denoted by alpha 1 Q alpha 2. Okay, where what is alpha 1 and alpha 2? So it is better understood with the help of this diagram. If you can see here diagram, okay, so this is a tape in which a set of symbols are written. Okay, so this will be your input initially. For example, so A0 to AN are representing your input symbol. So where if the head is located at AI, okay, this AI, okay, then you will be saying that before it, whatever things are there, that is your alpha 1, and what will be your alpha 2, including whatever will be read after this alpha 1 will be your alpha 2. Okay, so what is alpha 1, alpha 2? So alpha 1, alpha 2 together represent your whole string to be read by the Turing machine. Now, between this alpha 1 and alpha 2, you are representing one more information, that is the Q. What is it? So, Q is representing the state of the Turing machine when your head is at the AI. Again, repeating what it is representing. It is representing the state of the Turing machine, okay, in which it is when your head is locating this AI, the first symbol of alpha 2, and it is represented. So, from this, what you should understand that your current state when it is at AI is Q. Okay, so ID of M, this ID indicates that the current state of machine is Q and the machine head is about to read symbol AI from the tape. I hope this is clear. So suppose we are having delta Q comma AI is equal to star PL. So instantaneous description means at a particular instant, what is the description of a Turing machine? So description of Turing machine here, how we will describe this Turing machine? Current state is Q when the head is locating the AI, okay, or about to read AI. So if the function is written like this, so next instantaneous description of Turing machine will be change. Okay. So from this, what changes you have to represent? See, the Q state is changed to P, AI is changed to star, and your head is moved towards left. Okay. So if we have to represent this ID, then you will be replacing this AI with the star. Your head will be moving towards left, that is AI minus 1 position, right? And your state will be updated to P. Okay, so now your head will be locating AI minus 1. That is, it is about to read AI minus 1. So if you have to represent this with the help of a ID, so how you will represent? Your ID will get changed to A0. Now here you will be having P, right? And then you are about to read AI minus 1, and then AI is changed to star, right? And then AI plus 1 up to AN, right? So here it indicates the, see here also we have kept Q before AI, which is to be read. Here also we have kept this P state before AI minus 1, which is to be read. Okay, so in this way you have to represent the IDs of the Turing machine, which is showing the instantaneous that particular instant what is the status. Okay, so same thing with pictorially, it is represented for the same example for this one, right? So here it was a current ID. So we generally use this particular symbol to represent the Turing movement, next movement. Okay. So if this is departing two IDs, okay, this indicates what? This was the current ID and it was the next ID. So in next ID, see here P is written before AI minus 1 and AI was replaced by star and then This will be your alpha 2 now will be from AI minus 1, and alpha 1 will be up to AI minus 2. Okay, and pictorially it will be looking like this. AI is updated to star, head is here, and your current state is P. So similarly, if you have to represent the R, okay, instead of left movement, if it is moving towards right, then towards right, that means it will be moving to AI plus 1. You will be changing it to star, okay. So it will be like this, A0 to AI, okay. Since it is moved towards right, so before it you have to mention the uh, state information, and this will be your alpha 2. So I hope how to represent IDs for the Turing machine is clear to you. Now we will moving to the next part, that is the problem solving, which is of more importance. So before we start solving the problem, we will try to understand how the machines are simulated. Okay, so here whenever there is a functional matrix, we are having the information that is I, whatever allowable symbols, then S is number of states, and D is representing your movement directions. So we have to find out the purpose of aforementioned TM. Now this type of questions can be in TM, in the gate examination. They will give you the ID, ID information and the SFM, or they may give you the transition graph of Turing machine, and they will ask you, giving the multiple option, what is the purpose of this particular Turing machine. So how to understand the purpose of Turing machine? You need to simulate. Now without this initial configuration, no Turing machine output or information, that is the working, can be understood. So it is very much important and required that you should have information of initial configuration of Turing machine. So initial configuration here shown is that this is your input string to be read, and prior to this on blank the head is present with the current state alpha. Okay. So looking at this status, looking at this configuration, we have to simulate the machine. So we will start simulating. So this is your machine and this is your input. So how we represent this configuration? You can represent this with the help of this alpha blank. Okay, see here alpha blank 0001, and the output is bounded with the blank characters. So and then we are having this TM to represent next move likewise. Okay, so here we will check this or this, and we will try to simulate it. So if we want to simulate this particular Turing machine, how we will simulate? We'll have this blank, and in the on this blank we are having alpha state. It is 0001 and this blank. Okay, so now here alpha on blank is moving towards right. Okay, so in next move what we have to show is, we have to show this particular head is moved towards the right, that means here. Now when it is moving towards right, there is no other information available. This indicates that there is no change in the state, so the state will remain as alpha only. Okay, next is, now we are reading 0 with the alpha state. See here, alpha state with 0, again it is moving towards right. Okay, so here your head will be moving towards right, so this will be moving here and state remains the same. Next move you are having blank, so see There is again 0, 0, 0, 1 blank. So again it will be moved with no change in the state. Now next is we are having the fifth as now it is reading, it has moved, so blank 0, 0, 0, 1 alpha and blank. Okay, so if it is alpha and 1, what it is doing, it is changing 0 beta r. So now the state change will be the beta, and it is moving towards right. So and it is writing 1 to 0. So this one will get changed to 0. It will be moving towards right, and it is changing the state as beta. The still the machine working is not over, even though it has reached to the end of the string, that is whole string is red. Okay, in case of finite automata, generally if we end the string, we stop. Okay, but here even though the string is red, but we have not reached to a uh, halt state, and there is some transitions available here in the Turing machine functional matrix. So here beta on blank is moving to gamma. Okay, beta on blank is moving to gamma, and there is no movement. So here it will be not updated, as you can see here, no, nothing is written. So your head will remain here only because it is n. Only what has happened, the state is changed to gamma, and since you have reached to a hot state, your machine will stop working. Okay. Now, what is the observation? See, our input string was this, and now we have got a new updated tape content as 0, 0, 0, 0. What is the observation? So, whenever we have seen that the 0 is occurring, okay, continuously, it is just moving towards right. As soon as after 0 we got a first 1, okay, then what happened, we have replaced this 1 by 0. Okay, so the purpose of this machine will be what, if you get the 1 preceded by multiple 0, then change that 1 to 0. Okay, so this will be the purpose of this Turing machine. So I hope you have understood the working of the machine. What happened? Okay. Okay. So now we will be starting the problem solving. So very first problem we will solve will be very common problem, that is checking the well formatness of the parenthesis. So we want to construct a TM which will check the well formatness of a Turing machine. What do you understand with well formatness of a Turing machine? So formatness of a Turing machine means you are checking whether the number of left and right parentheses are occurring at the proper places or not. Okay, it is giving some meaning or not. That means for every opening there is a close parenthesis is available at a proper location. That is very important. Okay, so how we will be checking it? So the logic for this is, now here see a simple sample example is given, in which now see, I'll take a simple example here. At the first left parenthesis the state is Q0. This is the initial configuration, and we want to design a Turing machine which will check the well formatness. So how we will be checking? The logic for this will be, we will be, what is general way? We check that if there is a left parenthesis, its corresponding right parenthesis must present. Then again we check whatever is left parenthesis is there, its corresponding right parenthesis must be there. Okay, there can be many examples here also. The corresponding parenthesis for this is like this. Okay, so likewise checking we need to do. Now how we do this type of checking? What we will do, what logic will apply is, we will keep on checking the first such a left parenthesis whose right parenthesis will be very close. Okay, so what it means, see, this is also left parenthesis, this is also left parenthesis. So we will try to locate the left parenthesis which is the innermost, or the left parenthesis whose right parenthesis is very first. Okay, so as soon as we are getting left parenthesis, we are keeping on moving towards right to locate the left parenthesis which is closest one. So how we should get the closest one? So the closest one, in the sense, we will keep on moving. If we get the left parenthesis, as soon as we get the right parenthesis, this one, what we understand, that we have received the corresponding right parenthesis for one of the left parentheses. Now, which is one of that left parentheses that we want to locate? So, as soon as we get the right parenthesis, what we will do is, we'll convert this to a star. Okay, and we will try to search for its corresponding left parenthesis. Okay, so what we have done, we have keep on moving towards right to change the first right parenthesis. If we are getting left parenthesis, we are skipping, and we are getting first right parenthesis, we are making star, and now we want to locate corresponding left parenthesis existing or not. So as soon as we move towards left, we get this as a first left parenthesis. So what we will do, we will convert this left parenthesis to star again. Okay. So likewise our end marks are there. So you can use blank or any other end marks. Here the blank is used. Right. Now as soon as we do this changing the left parenthesis to right parenthesis, we will say that if we got one pair. Okay, now we want to repeat the same thing. So what we will do, we will again move towards, as soon as we convert it, we will again keep on moving right. If we get star, we will skip because it is already converted or it is already paired. Now you are moving towards right, and now you will be again locating. So you are repeating same step. What step? Locate the right parenthesis, make it star, and keep on moving left till you get the corresponding left parenthesis. As soon as you get left parenthesis, what you have to do? You have to convert this left parenthesis to star, 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 star. Okay, so you got now converted corresponding left parenthesis, and now your pointer will be moving towards right, because we don't know whether more right parentheses are existing or not. Okay, so it is keep on moving towards right if it is a star, star, star like this, and we will be reaching to, so we have not received any right parenthesis still, but we got the right hand mark. Now, as soon as we get the right hand mark, what it indicates? It indicates that all the parentheses are over, right parenthesis or left parenthesis. Okay, so you are this is not a decision yet, because it is possible that there may exist one more left parenthesis here, right? So we need to verify whether if you reach to right and mark, when you will revisit back, okay, whether you are also getting the left hand mark or not. Okay, so as soon as you get the right end mark, you'll be moving towards left. Moving towards left, if you get again a semicolon, that is at the left hand mark, so this indicate that it is a well formed parenthesis. Okay, now we'll check whether it will be true for this also. So here, what is the logic? The logic is, we will be trying to locate, if it is left parenthesis, we are moving towards right. We got a right parenthesis, we will be marking it as a star. As soon as we mark star, we trying to search for its corresponding left parenthesis. As soon as you get a left parenthesis, what we will do, we will make it star. Okay, as soon as you make star, you are keeping moving right. Okay, to like check for any more right parenthesis. Okay, so it is star, you are moving left, oh, sorry, right. Again you are getting left parenthesis, so you are not of interest, you are again moving right, you are getting this right parenthesis. So again what you will do, you will make it star and move towards left to locate the left parenthesis. Likewise, you will be converting this to star. Okay, and as soon as you convert it to star, you again move towards right. Okay, now it is the same situation as we had here. Okay, so again it will move right. Okay, and it will locate to check whether any more left parentheses are remaining, not remaining. If you also get a semicolon, that is a left and mark, it is the indicator of well formedness. So whether it is a nested parenthesis or whether it is a concatenated parenthesis, in both cases our algorithm works, our logic works. Now we'll try to check if we have the extra left parenthesis like this, how it works. So here it will work as what? Same way. Okay, we'll be converting this to star, moving left, making it star, again moving right, you got a semicolon. Now you will be moving left, left, left. Now what happened? While moving left, you got the left parenthesis for which there is no right parenthesis is existing. Okay, so here you will be replacing this with the decision as right parenthesis and you are halting. Okay, similarly, if there is a extra right parenthesis, so again your pointer is here. Okay, so it will be getting this, so it will make it as a star. Okay, moving left, making it star. Okay, then after moving they get making it star, it is moving right, star skipping, it is getting a right parenthesis, right? If it is getting right parenthesis, what you will be doing, you will be converting it to star and moving left to locate the left parenthesis, right? Now what happened, you moved here, 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 have you received any left parenthesis? No. So as soon as you reach here, you will give the decision that the right parenthesis is extra right parenthesis is existing. Got it? So now to design for this logic, okay, how we will be designing? So the designing will be, so what is the algorithm? So algorithm, let me show algorithm and then we'll design accordingly. So as we have said that every program, computer program can be represented with the help of Turing machine working. So algorithm is existing for all programs as well as algorithm is existing for all the solution which are provided by the Turing machine. So from the initial state, move to the right until you read first right parenthesis. Okay, replace this by star and move one position left. Now second is continue moving left till you read the first left parenthesis. Replace this with the star and move towards right. Same thing is explained. Repeat the above step till whole string is replaced by stars. Now while moving, now here is a twist. While moving right, if you come across the semicolon, okay, then move towards the left to search for any left parenthesis that might have been left unchanged. So if it is unchanged, so that is the indicator of if the parentheses are well formatted, there will be no more left parenthesis as I've explained, and the machine will only read the left and mark and it will be a OK case. Otherwise, it will be denoting the not OK case with the help of the result as extra right parenthesis, extra left parenthesis, and OK case is represented by O. So here, whatever symbols allowed on tape is written. So as we have discussed, what characters are possible on the tape, I will be having what? It will be having C, left parenthesis is there, right parenthesis is there, then star is there, then semicolon is there, right? This was already there in the input. Now, extra thing while processing, what is added? This is added. In input, you had left, right, and semicolon maybe. This was input. While processing, the extra symbol added was star. Then OK, LP, and RP. So these are the all possible symbols which are there on the tape. Okay, understood? Now is a question of how to design. To start designing and how many states will be there. So very first it is already given that there is a state Q0, right? Which is a initial state. Okay. So here, what was our working? Our okay case. Okay. So what we have done? Initial state was what we have done. If we are getting left parenthesis, we are moving towards right and we are not changing the state. No change is happening. Okay. State is not changing. Okay. Nor we are updating. So when there is a no change in the state, we will represent it with the self loop. So if you get the left parenthesis, what you are doing, you are only keeping on moving towards right. What I have done, I have simulated movement of this head from this position to this position, and since there is no change in the state of a Turing machine, we have kept this state as Q0 only, right? Next is we have read again left parenthesis, so same situation, so it is going to be in a same state. But as soon as we get a right parenthesis, there is a change happening. If there is a change happening, you should introduce a new state. For example, Q1. Okay. When this state is introduced, when you receive the right parenthesis, right? What changes you have done when you got the right parenthesis? You have replaced this with the star. right? So here change is what? Star. Then where you are moving after this? Making star, you are trying to locate the corresponding left parenthesis. So obviously you will be moving towards left. Okay. So state change here when it is this. What happened in the next case? What happened? Now you will be having case as what? Star moving towards left, and your state will be now Q1. Just now we have introduced this new state, right? Now as soon as you get the now see the earlier combination was opening bracket or left parenthesis with Q0, then you done nothing. But now the situation is, it is very important. When you got Q1 state and the left parenthesis, it is itself an indicator of that you already got a right parenthesis. That's why you have moved to Q1. Okay. So here, when you get a right parenthesis, what you will do? You will make it star and move towards left, and you are moving towards state Q1. When you are having Q1 state and you get a left parenthesis, what you are doing? You are making it star, and you are again going to do same thing. What same thing? You are again started journey to locate for the right parenthesis. Okay, which is as good as the case of this initial case. Okay, so what we need to do is, when you are in a Q1 state and if you get a left parenthesis, what you will do? You will make it star, okay, and move towards right. Okay, so what I've tried to simulate, I've tried to simulate, locate the right parenthesis, make it star, move towards left to locate left parenthesis. If you get a left parenthesis, you make it star and move towards right to do same journey. Okay, that is location of right and then corresponding left, which will be taken care by this again Q0 and Q1 state. Okay, so now see, you have moved back to Q0 when you have converted this to what? Star. Okay. Then this star was already existing. What you have done? You have moved towards right and you have moved to a state Q0. Right? Now see, there's a new situation. What is a new situation? If on Q0 you get a star, right? So this kind of thing is not yet reflected. Have you reflected? No, we have only reflected for opening and closing. But we got a new case. Which new case? This is a combination of star and Q0. Now in this situation, what we have done, if you get a Q0 and star, you do keep on moving towards right to locate a right parenthesis. We are not moving, we are not doing anything, we are not making any changes, right? So we can utilize same state for this representation as what? On Q0, if you get star, what you have to do? You have to keep on moving right and you will remain in the same state. Okay. Now what had happened? You got star, star, and you have moved to the right parenthesis with the state Q0. It is the same combination, see, same combination. So our same structure can be utilized. See here, when you will go here, you are already on Q0. When you get a right parenthesis, you will do this thing. You will move to Q1. Okay, you will make it star, right? And you will move towards left. And your state change was Q1 now. As far as this, okay, now you have again got a new situation. What is a new situation here? new situation is you are getting a combination of Q1 state with the symbol star, which is not yet defined in this structure. Q1 on only left parenthesis what to do is represented. But Q1 if get star, it is not yet represented in the diagram. So what you will do, what we have done, if you get a Q1 state the star, you are actually keeping on moving left because you are interested in locating the left parenthesis, right? So here you are keeping on moving towards left and it is a repetitive process. So here you will be having one self loop. So if on Q1 you get a star, you just keep on moving towards left. Got it? So you move towards left, you move towards left for all these stars and you have again located this left parenthesis with the combination of Q1. So this combination is already represented here. Q1 on left parenthesis, it is going to move to Q0. So till this, your structure is utilized, no problem, right? Now the situation will come as what? It will make now it as a star and move towards right? Here with the Q0 state. Now Q0 and star combination is already reflected. So keep on moving right. Okay. So it will reach here. Am I right? With the state Q0. Now what to do? Now this is again a new combination which is not yet reflected. So as per our logic, what we have done, if on Q0 you get a semicolon, we have done, can anybody tell me?
Ma'am, move left.
Then, so here if you get a semicolon and combination of Q0, we have not any reflection. So what we will do? We will have one more information. So here is a change. What we want to do? We want to keep on moving left. Okay. So while moving left, you can have what the location of extra left parenthesis, okay, or you can have a semicolon. So in this case, what we will do, we will have a new change in the state. Why new change in the state? Because here this semicolon is indicating the end of the string, okay, right? So here you will be, and after this the decision making will be happening. So here semicolon, you are moving towards left. Now as soon as you move towards left, okay, what happened? You have included one state as what? Q2. Okay. So you move to Q2 state now, moving left. Why this is required? Because this is in some different situation as compared to Q0 and Q1 working. That's why here now we are ready with, maybe we will be going for the conclusion, and that's why here we will be requiring a extra state Q2. Now Q2 on star, what to do? See what we are going to do. We are keeping on moving towards left till we get either left parenthesis or the left hand mark. So here, if it is a common thing which is repetitively happening, is what? If Q2 you are getting star, what you have to do? You have to keep on moving. When I say keep on, so it will be a self loop, for which case like this. Okay. Yes. So star left. Now we are keeping on moving star left. Now there is a possibility of having a left parenthesis or there is a possibility of semicolon. Since we are now considering a best case, okay case. So what happened in this case? We have reached to a semicolon. That is a left hand mark. So again this will be a concluding state, new state. So here after this Q2, if we get a semicolon, okay, we are giving okay case and we are stopping, no movement, and it will be a final halt state, right? We'll be reaching now halt state. So now whether it is a case of this or this type of problem, you will be reaching. If it is a case of this, then with the left parenthesis we move towards right, with right parenthesis we move to Q1, and making made it star and move towards left. Okay, now you got immediately the right parenthesis. Okay, sorry, left parenthesis here, left moving. So you again back to Q0 here. Okay, so these two are stars now, and now you are state Q0 star, keep on moving star star, right? Now you got a left parenthesis, keep on moving right. Again you will be going to do this as a star, making moving left left, you got this left parenthesis, you will make it star and move towards right. So here, since you got star, you will keep on moving right. Now you got a semicolon, you will be moving towards left. So all these are star, and keep on. If you are getting all star, you are keep on moving. You got a left parenthesis, you are reaching to OK case. So whether it is this kind or a nested kind, for both this machine is working. But we want to design a machine which will be able to give decision for all type of cases. What all type of cases? Now, as I've discussed, if it is having extra parenthesis, what should happen? So left parenthesis move right, left parenthesis move right, okay, right parenthesis. So here, see here Q0, Q0. Here the combination is Q0 and right. So it will be start and move towards left with the Q1, right? So again Q1 and star, you will be making it as star and moving towards right, semicolon, right? Now, which is a state here? It is a Q0 state after making it star, right? So here star and Q0, you are keeping on moving right. If you get a semicolon, you will be moving left with a change state as Q2. Okay, at Q2, if you are getting star, you are keeping moving left. Now the case is at Q2, you got new situation which is not yet reflected in this. Am I right? At the Q2 state, we are getting left parenthesis. So what will be the decision? The decision on Q2, if you get what left parenthesis, it is going to give the decision as what LP, okay, and no movement. We are stopping, we are giving decision LP, extra left parenthesis. Clear? Now we will be having one more case. That case will be, what will be the case? We will have now extra right parenthesis. Okay. So here what will happen? It will be made star. Again it will be made star. Okay. And you are keeping on moving here. So here you'll be having combination of Q1 or Q0 and this. So you will be making again a star, okay, and moving left at and state is Q1. So Q1 star keep on moving. Now the situation will come, new situation, that is Q1 and the semicolon. Got it? Whether we have reflected anything like this, Q1 star is reflected and Q1 left parenthesis is reflected. Okay, only two cases. This one and this one. but this combination is not yet reflected in this machine. So what you will do now here, semicolon and combination of Q1, then what is your decision? Decision is, so if on Q1 you gave a semicolon, the decision is there is a extra right parenthesis and you will have no movement and you will void. Okay, so this semicolon will be replaced by RP. Got it? So now your machine is ready. Whatever you have thought of making it work, okay, you have tried to reflect it to the machine. So while designing machine, what you should do very first, your algorithm should be clear. And second thing, you should consider all cases, okay, step by step to complete this machine. So I hope this problem is clear to you. Okay. So we'll be moving to the next problem. So once you draw this machine, you can easily convert it to or represent it with the help of a simplified functional matrix. But it is must that you should consider all the symbols, input symbols. If there is no movements, you have to just give the dashes. So now, second very common problem, which is I think there is one more complex problem. You just tell me whether you want the multiplication problem to be discussed or this problem where the language a raised to n, b raised to n can be recognized by Turing machine. You give me choice, accordingly I'll discuss. What do you want? Multiplication. Okay. So we'll discuss now the problem of multiplication. Okay. So we want to construct a Turing machine which will be designed to multiply two unary numbers. Now here we'll be talking about unary numbers. So unary numbers, I hope you understand unary. What do you mean by unary numbers? So the number system in which only single symbol is used is a unary system. Okay. So here in this case we have considered the unary symbol as 1. Okay. Now, what is the initial configuration? The initial configuration is very important. For multiplication, we will be requiring the two operands. First operand is multiplier, another operand is a multiplicand. Okay. So here the symbols which are used are, one is for representing the unary symbol. The comma is used as a separator between multiplier and multiplicand. The semicolon is used as the and marks of input. Okay, and the as it is an infinite tape, the other after this semicolon we have utilized the tape to store the result. So here the result is stored. So initially this is all blank, nothing is there. Okay. So here you'll be having a structure or instantaneous description or initial configuration as this. Now we will have a logic. So whenever we are multiplying any number with any other number, what we do generally in decimal cases, suppose we are having 2, 3 into 1, 2. So what we do? We do multiplication with this and then this, okay, and that intermediate result is stored, and then again we do multiplication with this and this and this, Okay, and result is stored, and then we do summation. Like this is a normal process. Same to same process we have to represent here. Since it is a unary number, now I can have any number of 1 here, any number of 1 can be there. So what will be result? So very first try to understand this 1 is representing 2. Am I right? Similarly, what happened? Multiplication 1 1 1 comma 1 1 4. Abhijit, what you want to send? Tell. Should I take that number for multiplication? 1 1 1 or 1 1 1? Yeah, result is 4. Definitely. Um, will it be okay? This example or some other number is to be taken. So otherwise, I'll continue. Yes. So here, this is 2. This is also 2, right? So here 1 will be multiplied by this as well as this. This will going to give you result as 1 1. Similarly, this 1 is going to multiply these two numbers. Okay. So this will also give you result as 1 1. Right. Now 1 1. This 1 1 is added, then it will become 2. But since we don't have binary like uh, 2 is represented as 1 0 in binary, right? Because there are two symbols, but in unary the 2 will be represented like this. Okay, so the 2 will be like this. The carry forwarded is also 1. One is kept and one is carry forwarded. Okay, so now 1 1 again 2, so this 2 will be represented by this 2. So how many ones you got here? 4. So is it a correct answer? 2 into 2 is equal to 4. Okay, so same logic we have to use. Here we have used a symbol as 0 for initial release. So what is the logic? See the algorithm. Replace 1 of the multiplier by 0, that is subtract 1 from multiplier. This is your multiplier. Why to subtract? To indicate. See, when we are doing it manually, we know that the turn of this 1 is over. Then there will be a turn of that next one. But to the machine, to the computer, how we will indicate that the turn of this 1 is over? By making it as the 0. Once its turn is over, we will make it as 0 to indicate its turn is over. Okay. So what we are doing, replace one of the multiplier by 0, that is subtract 1 from multiplier. To add the multiplicand to the result area, that is beyond the right hand mark, replace 1 of the multiplicand by a. Okay, what we have to do? We have to do the here to add the multiplicand. Now we want to add this multiplicand. Okay, so to the result area, that is beyond the right hand mark, replace 1 of the multiplicand by a. So this is your multiplicand. It will be replaced by a. Find the end of the result where 0 can be found. Here, replace it with the symbol b. Here you will be writing b. Result is represented by b's. Okay. So here this will be converted to a to show the turn of this multiplicand. This multiplication is also over. This is multiplied by this is also over. Will be represented by a. With the example, I'll explain. Okay. Next is, and you will be writing here b to represent the result. Now repeat the aforementioned step 2 and 3 till all ones in the multiplicand are all replaced by a's. That means for this one, see, for this one, you are replacing these two a's, okay, and this two b's, okay, so that we can say that turn of one multiplier bit is over with the multiplicand. Now once it is written, we want to also do same thing for the next bit. So we need to again replace this a by 1. Okay, and then we will do again the multiplication and we will add bb here in this area. So for that, what is written? Repeat the aforementioned step 2 and 3 till all ones in the multiplicand are all replaced by a's. The multiplicand is added once to the result area. Hence, reset the multiplicand to all ones. As I have told you, a's will be reset to ones again and repeat the step starting from 1. Stop when all ones, these ones, all multiplier ones, these multiplier ones will be replaced by 0. And in this way, your multiplication will be over. Now see here, the example is written here. We will also do this example. See here, initial configuration was 1, 1, right? Your head is on separator and 1, 1. It is the initial configuration. So what we will be doing? Very first, what we have to do? We have to take this as first, that is list significant bit of multiplier and make it 0 so that we can proceed further. So we will be moving left. If alpha and 1 is there, then we will be making it as a 0. Okay. After making it 0, what we have to do? We have to convert the multiplicand bits to AA. Okay. So how it will be giving? You will be moving towards right after making it 0 and making it as A, moving again right and making it as A, and then you have to also write it to the result area, okay, as B B. For every 1 1, you have to also write BB corresponding to as many multiplicand bits are there. Okay. Once you write it, what you will do? You will be again coming back. Okay. Since the work is over, what work is over? For every corresponding multiplier bit, for a multiplicand bit, you have written the output. Now what we need to do? We need to replace this one AA by 1 1 again. Okay. Why? See here we have changed it to one AA. Now since we want to remain with multiplication with this bit as well, so for logic it will look for only 1 1. It will not look for AA. Okay. So once you write here BB, you have to come back and convert back or reset AA to 1 1. Okay. Once you reset it, you'll be moving towards left. If you get 0, it is an indicator that it is the just considered multiplier bit. Okay, and immediately before it, whatever one is there, you have to replace it by 0. There may be mini multiplier bit. Okay, so you have to move to the one which is just immediate to this 0. Okay, you will make it again 0 and you will repeat this process. So this is a logic. Now for this logic, we have to design a machine. So how our machine will look like? Now see what I'll do. Very first, how many symbols we have used here? 0, 1, A, P, semicolon and this. Now we don't know how many states will be there. Okay. So what we will do, we will start with initial state. So initial state was alpha. Okay. And what we have done at alpha, if we get a semicolon, if we get a comma, what we have done, we have moved towards left. Why we have moved towards left? Because we want to do what? We want to convert this multiplier 1 bit to 0. So at alpha, so there is a change, right? If there is a change, what you have to do? You have to change the state. So on alpha, if you get a comma, you have to move towards the left. Okay, so you have just moved towards left when you get a comma. There is no change in the state. This case, right? Now, when you move towards left, you got 1. So here is a change. Okay. So you need to change the state. So alpha on 1, what you have to do? You have to make it as 0. Right? You have made it as 0. See here. And then you will be moving towards right. Right? So you change state as beta. What I have reflected now with this, alpha on comma is moving towards left. Okay, and in the same state it is there. On 1 it has made change and moved towards right. Now beta and the here. You got a combination as what? Beta and comma. What to do? To get a beta and comma, what you should do? You should see beta and comma, you should move towards right. We are also moving right. You have to move towards right. So here, move towards right. Now after moving right, what you have got? You got 1 and state is beta. Okay. So here, what you have to do? You have to make it change as what? A. So beta on 1 need to be changed as A and keep on moving right and do the same process. What process? If you get 1, you need to make it as A. So can I take it as a self loop? If you get 1, you make it as A and move towards right. Okay, see here. On beta, if you get 1, you have to remain in the same state. You have to make it as A and you have to make it as, you have to move towards right. Now, after doing this, what you have to do is, you will be keeping on replacing 1 by AA. Now you got a semicolon. Now, as soon as you got right and mark, what you have done? Yes, as soon as you got a right and mark, you have to replace these zeros by VB. Okay. So if you get a semicolon, you have to, on beta, you have to move to a state the beta on semicolon. You are moving to a new state because there is a end mark. Okay. New state as gamma and you are moving towards left, and what you have done, you have converted, see here, you have converted back this AA to 1 1 at a gamma state. So here you move your semicolon towards left and move to a gamma state. At gamma state, see, when you are here, you move here. Okay, at a gamma state, this one. You have replaced this by 1 back. Okay, so now you replace by 1. So at gamma, if you get A, then you are replacing it by 1 and moving towards left. What you are doing? You are replacing A by 1 and moving towards left. Till what you have to do this? Till you get this comma. Okay. So here at semicolon, at the gamma, you move 1 minute. What else? At beta, at semicolon, you move to gamma and move toward left. At gamma, if you get A, you have replaced it by 1 and you change the state as the delta instead of the remaining in the gamma state. Why to do this? For this 1, when you will go to delta state, so 1 and right, for every 1 you have to replace it by b. Okay, so now at the delta, if you get 0, you'll be making it as b. So instead of continuously making it a, what is done is here we will be having a state as b. At the gamma, if you get a, you are replacing it by 1 and moving towards right. Why you are moving right? Because you want to, for this one corresponding, you have to write in a result area as b. Okay, so you at gamma, if you get a, you are moving to a state delta, making it as 1 and moving right. At delta, if you get what, semicolon, then what you will do, you will be at a delta state and keep on only moving right. Okay, next at the delta, if you get 0, then you have to make it as what, this 0 will be replaced by 1. This 0 will be replaced by B, and then we have to move again back here and make it as A. Again you have to come back and make it as B. Like this switching you have to do. Okay. So at delta, if you are having semicolon, you have moved towards right. If you get 0, then you have to make it as B. This 0 will be converted to P. So at the delta, you're moving again to a new state that is nominated as epsilon. And here what you have done, if at the delta you get a 0, you'll be making it as V, and you'll be doing what? You are moving towards left. Okay. Now at this state, that means once you move towards left, what you will get? You will get a semicolon. So as soon as you get a semicolon, you are keeping on moving left. Why to? Because we want to locate this A, right? So now again, if you get 1, what you have to do? If you get again 1, you have to keep on moving the left, because what you want to locate this A. Okay. As soon as you get this A, what you will do? You will convert it to 1, right? You will convert it to, at this state, if you will get 1, you will get convert it to A and move towards right. Now why to move to this delta state? Because now the thing is repeating. Which thing is repeating? The delta, whatever we have done with this delta, what we have done, we have replaced this 0 by b. So once you read this delta, what will happen? Now the situation will be what? At empty, you got the what 1. If you got 1 minute, you have got A. uh If you got A, you made it as 1 and move towards right. Right? Now this A is replaced by, see here, this A is replaced by 1. Okay? And now you are moving towards right. So now when you are moving towards right, what will happen? Now to this delta you are getting 1. So whether we have written any such situation delta on 1, we have not yet reflected. So when there is a delta on 1, what we need to do, we have to keep on moving the right, because we want to convert this, right? So here, so when it will get 1, it will keep on moving right. If it will get B, then also it has to keep on moving right. Because what we want to do, we want to locate a 0 in the right hand side. Okay? So now at the delta, as soon as we get to 0, so same thing will be get repeated. So in this situation, we have added two transitions. One is this and another is this. Okay. Now with this, what happened for this 2? We have replaced this 2. Once it is replaced, so what will happen now? It will move, making it as B, it will move left. After moving left, if it is getting B, now see, one first time it is getting B at empty, uh, that is epsilon. So if we are getting what B, then you have to add here what you have to keep on moving towards left. You move towards left. You move towards left. Now, if semicolon, it is already indicated left. If it is 1, then also it is indicated 1. So it will keep on moving left, left. Now the new situation will be this one. What is the delta, sorry, epsilon and the comma. This is not written anywhere. Now epsilon and comma, if this is the case, then what you will do, you will be moving to a state that is alpha. Why? Because 1 minute. Wait, please don't leave. 1 minute. I hope I am audible. Yes. So please don't leave. I have to share the link for feedback, which is compulsory. 1 minute. Okay, I'll send you the feedback link. Let me complete this problem. It takes some time. Okay, so I was discussing this. So finally, we were at so here finally what we have done, we were at this particular problem, we have converted this. Now when we will get a comma, when we will get comma at this particular state, you will be moving to a state alpha with no movement. Okay, now here at this situation, you are at the finally at alpha state, which is as good as your initial state. Okay, so hereafter you have to continue. What you have to continue now, the situation will be what? At alpha, you are getting 0. So if you are getting 0, then you have to add on the things as what? You have to just keep on moving left like this. Hello? Yeah, wait. I think some connection issues are there. I hope you have understood whatever problem is discussed for multiplication of unary numbers. If you have any other point to be discussed, please let me know. Okay. So I am here sharing this link. Just fill this particular form. So Abhijit, Yash, have you understood all the things which are discussed? Okay, so Nisha, Abhijit, and whoever were present, if you know them, just inform to fill this form. Okay. Any other discussions you need? I think it is getting started. 1 minute. Yes. See, actually, this gate PDF you must be solving. Okay, so for CSL, you already know the structure of a grammar. In that case, the left hand side and right hand side. So in left hand side, you will be having same means whatever number of non terminals are present in left hand side, at least that many non-terminals must be present in right hand side, and extra of it can be there. So if you want, I can explain you example. If you want to stay, I can show one example. 1 minute. I think in the PPT I have shared with you. 1 minute. Just wait. I'll open that particular. Okay, Yash Samant, are you from IT? 1 minute. Okay, I'll share on your Google Classroom all the PPTs. Let me check the PPT. Okay, will it be okay if I'll share PPT with you? 1 minute. I think it is opening. Yes. Kept one example here. No, it will be in grammar actually. 1 minute. Not able to locate. I had one example in my PPT. Mm, it is not updated one or one. Okay, I'll locate and share with you. I am having one example with me. Okay, let it be. I'll share with you. Okay, that PPT. Or if you want, I'll conduct one session. You just inform me. I'll try to conduct the session for whatever required things you wanted. One more thing, I hope this paper you know, and you are solving many papers, gate papers. So try to solve this paper. I'll share this paper as well on your gate. This here there is also a solution below it. So if you find any difficulty, you just inform prior to, so that I'll try to solve your difficulty. So all these problems are having solutions. So likewise, you'll get many more PDFs online where you can search for your contents related to theory of computation. So I hope this session was uh, of use to you. I was talking, but my mic was off. Yes. So I think uh, this session was fruitful to you. Yes, I'll share with you the PPTs on the Google Classroom, Gate Classroom, and you will find the details on it. My videos are also available on YouTube. Just search with my name and theory of computation. You'll find all the videos there. And apart from this, if you want any more discussions, please let me know. I'll try to cover that. Okay, thank you. I think I should stop. I will share with you the PPT. Okay, is it okay? Okay, thank you.